Imagine putting the world's most advanced artificial intelligence into like a rescue drone
Right.
and you fly it out into this massive rainstorm to search for a stranded hiker. It's navigating beautifully,
Well, yes.
processing the wind, the rain, the terrain.
Doing exactly what it was trained to do.
Exactly. Until one single optical sensor gets a little wet and sends a burst of noisy glitch data to the processor. In a traditional system, that tiny bit of mathematical noise just cascades.
Oh, completely.
The neural network encounters an input it doesn't recognize, the system freezes, and your incredibly expensive hyper-intelligent drone just drops out of the sky.
And that is the fragile reality of modern AI. I mean, we are so used to interacting with these systems while they live inside giant climate-controlled server farms, right? With virtually infinite power and perfect data pipelines.
Yeah, the cloud.
Right, the cloud. But when you take them out of that perfect environment and put them at what we call the physical edge.
Like in drones or rovers or just mobile devices.
Exactly. When you put them there, their underlying architecture becomes this massive liability.
Which is exactly the flaw we are looking at today. So for you listening, our mission on this deep dive is to give you a shortcut to understanding a radical and frankly kind of mind-bending mathematical paradigm that could completely solve this bottleneck at the edge.
It really is a paradigm shift.
It is. It's called hyperdimensional computing, or HDC.
Okay.
And to unpack this, we have a really fantastic stack of sources in front of us. We've got an introduction to HDC designed specifically for robotics, a deep dive comparative study between HDC and standard neural networks, and the foundational papers by Pentti Kanerva on cognitive modeling with high-dimensional random vectors.
Yeah, and to even start to understand what Kanerva and these researchers are doing, we really have to fundamentally shift how we think about computing. I mean, since the 1940s, we've lived under the von Neumann architecture.
And just to clarify for the listener, when we say von Neumann architecture, we're talking about like the standard way every laptop and phone works right now, right? Central processing unit, separate memory, computing with exact zeros and ones.
Yes. Highly precise sequential logic. Even modern deep learning neural networks, which, seems so fluid to us, they still operate on strict tensors and scalars.
Meaning they need perfect math.
Right. They are making highly precise floating point calculations where literally every decimal place matters. But hyperdimensional computing asks us to just leave all of that behind.
Just throw it out.
Throw it out. We are moving into a world where information isn't a precise number, but a massive 10,000 dimensional holographic vector.
Okay, let me see if I have this, because before we can talk about how this computer thinks, we really have to talk about where it thinks.
The space itself, yeah.
Right, we have to wrap our heads around the weird geometry of a 10,000 dimensional hyperspace.
Which is hard because human brains are hardwired for 3D space.
Oh, absolutely.
When we try to visualize 100 dimensions, let alone 10,000, it usually just leads to a headache.
Yeah, I'm getting one right now, just trying to picture it.
Right. But the mathematical properties of this specific space turn what data scientists usually call the curse of dimensionality into an absolute blessing. It all comes down to how distance works at that scale.
Okay, how so?
Well, in low dimensional space, like a flat 2D piece of paper, if you want to place 2 points so they are completely unrelated.
Like orthogonal to each other.
Exactly. Orthogonal, if you want to do that, you have to place them very intentionally.
Like actively drawing one dot in the bottom left corner and deliberately drawing the second dot in the top right.
Yes. But in a 10,000 dimensional hyperspace, the volume is so incomprehensibly vast that the geometry actually warps our everyday intuition. If you pick any random point in that space, 99.9% of the total surface area of that space sits at the equator relative to your point.
Okay, wait. Let me try an analogy here to ground this for the listener, because that's wild. If you're in a tiny, cramped room, it's actually really hard to stand far away from someone. You have to actively press yourself into opposite corners to get any distance.
That's a great way to look at it.
But if you're floating in an infinite, sprawling universe, and you pick a completely random spot to teleport to, you are mathematically guaranteed to be millions of miles away from anyone else. Like, the space is just too big for accidental crowding.
That analogy perfectly captures the mechanism. I mean, if you generate a 10,000-bit vector completely at random...
Which literally just means flipping a crane 10,000 times to get a string of zeros and ones, right?
Yes, literally just a random string.
Right.
And you do that, and then you do it again for a second vector. The math guarantees those two vectors will be completely unrelated to each other.
They'll just naturally be orthogonal.
Exactly. You never have to worry about running out of unique, distinct concepts.
So apply this to the real world for me. If we're putting this architecture in a robot on Mars or, that drone flying through the storm we talked about, why does floating in this vast space actually matter for the physical hardware?
It creates extreme fault tolerance. Think about the distances again. Any two random vectors in this space are naturally going to be about 5,000 bits apart.
Meaning they differ in about half their dimensions.
Right. And this distance makes your data practically indestructible. Let's revisit your drone in the storm. Say it has a vector representing a navigational concept and a sudden power surge or like a radiation spike hits the memory chip.
And the hardware gets physically corrupted.
Exactly.
Because in a normal von Neumann computer, if a bit flips in a crucial system file, you just get the blue screen of death. The program crashes because it's looking for an exact sequence of code that no longer exists.
But in HDC, let's say that radiation spike causes 33% random noise across the vector. That means 3,333 bits out of the 10,000 are completely flipped from a 1 to a 0, or vice versa.
So the vector is deeply corrupted at that point.
Deeply corrupted. But mathematically, that corrupted vector is still geometrically closer to its original perfect source vector than to literally any other random vector in the entire universe.
Wow. Because it would need to have over 5,000 bits flipped to even cross the halfway mark toward being mistaken for a different random concept.
Exactly. Which means the noise just gets swallowed by the sheer size of the space. And from an engineering standpoint, this is a massive win.
I can imagine.
Because the data representation is inherently robust, our sources indicate you can actually drop traditional error correction mechanisms from the hardware entirely.
Wait, really? You just don't need them?
You really don't. This allows for a 25% reduction in compute costs at the edge right out of the gate, because the system no longer has to constantly double-check its own math.
Okay, so having indestructible data is great if you just want to safely store it in a rover on Mars. But, storage isn't thinking. Random noise is just noise.
Right, you need to compute.
Yeah, if we want this system to actually compute, how do we combine these giant vectors without losing the information inside them? Like, how do we turn this noise into an actual cognitive structure?
We use what are called vector symbolic architectures, or VSAs.
Okay.
These provide mathematical operators to combine random vectors into complex thoughts. There are basically three main algebraic operators that mimic cognitive functions, and the first one is bundling.
Bundling, okay.
Mathematically, bundling is a form of addition or superposition. You take several 10K dimensional vectors and add them together to create a set. The crucial part is that the output vector is geometrically similar to the inputs that created it.
Superposition.
Yeah.
Okay, think about playing a piano.
Okay.
If I press a C, an E, and a G at the same time, I bundle those sound waves into a single C major chord. It's one unified sound, but the result still contains the harmonic flavor of the individual notes. Like you can still hear the C inside the chord.
That paints the picture really well. You are combining items into a single container while preserving their original identities. The second operator is binding. Now, this is a form of multiplication. In binary vectors, it's typically done using an element-wise XOR operation. Binding is used to create an association, like linking a variable to a value.
Whoa, hold on. XR. For the listener who hasn't taken a computer science class in like a decade, what does an element-wise XOR operation actually do to these vectors?
Fair question. It's essentially a logic gate that flips bits based on whether they match or differ. But conceptually, it might be easier to think of it as a cryptographic lock.
A lock, okay.
Yeah. When you bind two vectors together using XOR, the resulting output vector is entirely dissimilar to both of the inputs. It's totally orthogonal.
So it hides the original data.
Precisely. So if you have a vector for the variable color and a vector for the value red, and you bind them, the resulting vector doesn't look anything like color, and it doesn't look anything like red.
It creates a completely unique locked concept of color is red. And you can't see the original pieces just by looking at it.
Right. Until you apply the mathematical key, which we will get to in a second. But first, the third operator is permutation.
Okay. Bundling, binding, and permutation.
Yes. Permutation is simply a cyclic shift of the bits. You literally just move every bit in the 10,000 dimensional array one position to the right, and you move the last bit to the front.
Wait, what does shifting bits accomplish?
It protects the order of things. Shifting a vector makes it completely dissimilar to its original unshifted self, so it acts as a tracker for time or sequence.
Okay.
The vector for A, shifted once, means A is in the first position, shifted twice. A is in the second position.
Wait, okay. If we were bundling sets binding variables and shifting for sequence, and we are constantly cramming all this overlapping data into one single 10,000 bit array. Doesn't it just become a muddy, compressed mess?
It sounds like it would, right?
Yeah. Like if I have a massive data record of a person, their name, age, height, all bundled and bound together, how on earth do you extract a specific, clean piece of data back out of that?
That is the core challenge of hyperdimensional math, and the solution relies on something called an item memory or a cleanup memory.
Cleanup memory.
Right. Let's go back to that cryptographic lock. Say you bound the variable name to the value Alice and then bundled that lock into a giant record vector containing age, height, and everything else.
Okay.
To query the name, you mathematically unbind or multiply the giant record by the name variable.
So I apply the key to reverse the lock.
Yes. But because that master record vector contains all the other bundled junk, the age, the height, the math doesn't give you the pure Alice vector back. The output is a highly degraded, noisy version of the Alice vector.
Like static on a radio station. You can kind of hear the song, but it's obscured by fuzz.
Which is exactly where the geometry saves us again. Because we are in 10,000 dimensions, that noisy, static-filled vector is still geometrically closer to the pure Alice vector than to any other concept.
Oh.
So you pass that noisy output through the cleanup memory, which is basically an associative dictionary of every pure vector the system has ever defined.
Oh, this makes perfect sense. Think about when you're reading a text message from a friend who is typing way too fast, and they spell the word definitely as DEFINATLY.
Yeah, totally garbled.
Your brain acts as a cleanup memory. You see the noisy, degraded word, you instantly cross-reference it with your mental dictionary, find the nearest correct match, and you read the word definitely without even pausing.
That is precisely the mechanism at play. The cleanup memory finds the nearest perfect vector, filters out the mathematical noise, and instantly restores the pure value.
That's brilliant.
It really is. This allows you to compress incredibly complex hierarchical data structures into a single array and still reliably extract exactly what you need.
So we've built this robust, noise-tolerant memory system, but how does this actually stack up when we put it head-to-head with the reigning champion of modern AI, deep learning? Because we know neural networks are dominating the industry right now.
Right, and this is where the comparative study in our sources provides a really fascinating perspective. HDC isn't just some alien logic. Mathematically speaking, a canonical HDC model is homologous, meaning it is functionally equivalent to a highly compact two-layer neural network.
A two-layer neural net. Wait, standard deep learning uses hundreds of hidden layers to process information. Two layers sounds incredibly primitive.
Well, it is much simpler. In this mathematical equivalence, the encoding phase of HDC, where you map features into vectors, acts just like the input layer of a neural network. Except instead of constantly updating and tuning the weights during training, the weights in HDC are completely frozen, random values.
Frozen weight, okay.
And the inference phase, where you compare your query to the cleanup memory, acts as the final classifier layer.
So if it lacks hundreds of layers, the big difference has to be in how it learns. Traditional deep learning relies on gradient descent. It cranks through thousands of training epochs, taking massive data sets and nudging tiny decimal weights over and over, consuming literally megawatts of electricity to slowly learn a pattern. How does HDC learn without doing that?
HDC completely abandons gradient descent.
Wow.
Yeah, it uses something researchers call approximate backprop, which relies on simple vector arithmetic. Let's say the system misclassifies an image of a dog, thinking it's a cat. In deep learning, you'd have to calculate the error gradient and slowly backpropagate that calculus through millions of nodes.
Right.
In HDC, the system just takes the query vector, the image it got wrong, subtracts it from the cat prototype vector, and adds it to the dog prototype vector.
Wait, I want to make sure I'm hearing this right. If it gets an answer wrong, it literally just subtracts the 10,000-bit string from the wrong category pile and adds it to the correct category pile, and that's the entirety of the learning process.
That is the entirety of it. The learning rate is essentially set to 1. The associative memory updates instantly.
That's crazy.
Enables rapid, completely transparent, one-shot learning. You don't need thousands of iterative loops. You show it the data, it adjusts the vectors via addition and subtraction, and the system learns the new pattern on the spot.
Okay, I have to be the skeptic here for a second.
Go for it.
If this math is faster, completely transparent, runs natively on low-voltage hardware, uses a fraction of the power, and learns in one shot, Why isn't Google running everything on hyperdimensional computing right now? Like, what is the catch?
The catch is the complexity wall, and the research sources are very clear about this trade off. HTC is phenomenal at certain tasks. On simpler data sets, like the MNIST database of handwritten digits, an HTC model derived from a neural net hits about 96.7% accuracy. It performs admirably.
Okay, so it works on the basics.
Yes. But when you throw highly complex, nuanced data at it, like the CIFAR 10 dataset, which contains complex color photos of airplanes, birds, trucks, and animals in different lighting and backgrounds, HTC struggles significantly.
What does it hit a wall there?
Think about how deep neural networks work. They use those hundreds of layers for deep, nonlinear feature extraction. The first layer learns to see an edge, the next layer combines edges into a shape.
The next layer combines shapes into a bird's beak and so on.
Precisely. Because HDC is mathematically equivalent to a shallow two-layer architecture, it physically cannot build that hierarchical understanding of a complex image. On the CFAR 10 dataset, this baseline HDC model only achieves about 51% accuracy.
51%. So for a complex visual scene, it's basically just flipping a coin,
Essentially, yes.
which means you are trading deep learning's ability to untangle incredibly complex visual or linguistic nuances for extreme energy efficiency and robustness.
Correct. You wouldn't use HDC to generate a photorealistic video or write a novel, but you would use it for a robot that needs to survive in the physical world and learn on the fly.
Which perfectly sets up the real world applications in our sources.
Yeah.
Let's talk about how this actually helps a robot navigate. One of the experiments dealt with viewpoint invariant object recognition using a data set called ALOI.
Ah, yes.
They had a robot trying to recognize a teddy bear from multiple different viewing angles.
Right. In a traditional computer vision system, recognizing that bear from a new angle usually means storing a massive database of reference images. When the camera sees the bear, the processor has to run a heavy similarity search, comparing the live feed against the 0-degree image, then the 15-degree image, then the 30-degree image.
Which sounds incredibly computationally expensive.
It is. But with HDC, they didn't do that. They used that bundling operator, the superposition we talked about earlier. They took the 10,000 dimensional vector for the front view of the bear, the side view, and the back view, and literally just added them together into one single monolithic teddy bear vector.
And because that single bundled vector inherently contains the features of all the viewing angles simultaneously, the system only has to make one single mathematical comparison to recognize the object.
Exactly. You aren't searching a database, you are measuring distance to one master vector. Furthermore, because of the continuous geometry of the hyperspace, the bundled vector actually offers better interpolation between the known angles.
Oh, wow.
So if you show it a 45-degree angle it has literally never seen before, the bundle is mathematically robust enough to fill in the gaps and recognize it anyway.
Squeezing multiple viewpoints into a single object representation saves massive amounts of compute, which leads directly into the SexLam example, navigating the Nordland train routes in Norway.
This is a remarkable demonstration of the permutation operator shifting the bits to track time. Place recognition is notoriously difficult for robots when the environment visually changes. The researchers had video from the front of a train driving a 700-kilometer route in Norway during the spring. The goal was to have an algorithm recognize those exact same places from a video taken during the dead of winter.
Spring to winter. That is a massive visual shift. You're going from green grass and exposed rocks to a landscape completely blanketed in white snow. A pixel-by-pixel comparison would fail instantly.
Instantly. Traditional algorithms attempt to solve this by matching scalar similarity matrices frame by frame, which requires heavy computation. But with HTC, they didn't look at isolated frames. They took a sequence of places, permuted them, shifting the vectors to lock in their temporal order, and then bundled them together.
So instead of the computer trying to match tree and then looking for rock and looking for lake, it shifts and bundles them to create a single unified concept of the experience of passing the tree, then rock, then lake.
Yes.
It literally compresses a sequence of time into a single spatial vector.
Exactly. And by replacing heavy matrix multiplication with simple vector sequence bundling, HTC reduced the computational operations by a factor of 10 while maintaining near identical accuracy to the power-hungry methods.
That is incredibly elegant. But the sources don't just stop at sensory perception and mapping. They actually delve into abstract thought and analogical reasoning. And this is where we see the binding operator, that cryptographic XOR, lock really shine.
Yes. Let's look at the dollar of Mexico test. This is a classic computer science test of symbolic reasoning, basically asking a machine to understand analogies.
Okay.
To do this in HDC, you build two records. Record A represents the United States. You take a vector for the concept of country and bind it to US. You take a vector for currency and bind it to dollar. Then you bundle those two locked pairs together. Record A is now the holistic mathematical concept of the US and its currency.
Okay, I follow. And record B is Mexico. Bind country to Mexico, bind currency to peso, and bundle them into a single record. In traditional symbolic AI, if I wanted the computer to figure out the Mexican equivalent of a dollar, I would have to write explicit rigid code, right? Like, if country A has this relationship to currency A, find the matching variable in country B. The manual logic tree.
But in HDC, analogical reasoning becomes a native mathematical operation. You don't write an if-then rule. You simply multiply record A by record B.
Wait, really? But wouldn't multiplying two massive bundled records just scramble the data entirely? How does the system know it's supposed to map dollar to peso?
The math naturally forces the answer out. When you multiply the records, the shared variables, the country vector and the currency vector, mathematically interact and cancel out their noise. It instantly creates what Canerva calls a holistic mapping vector. The system infers the structural relationship without explicit programming, automatically mapping dollar to peso.
Because the algebraic structure of the 10,000 dimensional space naturally mirrors the logical structure of the analogy.
Yes. And the performance metrics back this up beautifully. When researchers ran HDC on Raven's progressive matrices, which is a standard test for abstract visual reasoning and pattern completion, HDC achieved 88% accuracy. Standard artificial neural networks only hit 61%.
Wow. And beyond accuracy, the speed is what really stands out here.
Yeah.
The sources note HDC performs this analogical reasoning 250 times faster than traditional symbolic logic engines, purely because it isn't running through endless loops of if-and statements. It's just multiplying two giant arrays of bits in memory.
It fundamentally changes what it means to compute an idea.
It really does. So, bringing this all together for you listening, the journey we've taken through these papers is profound. Hyperdimensional computing takes what is usually a curse in data science high dimensionality and turns it into a geometric blessing.
Absolutely.
By operating in an incomprehensibly vast 10,000 dimensional space, it ensures that data is inherently distinct and incredibly resistant to physical hardware failure.
And by utilizing three simple algebraic operations, bundling for sets, binding for associations, and permuting for sequences, it can compress complex hierarchical data, temporal sequences, and even analogical logic into a single uniform array.
Right. It isn't going to replace the massive deep learning models generating art or writing code in the cloud, but it provides a fast, resilient, and transparent alternative that runs natively on edge devices. It drops the power budget, drops the data requirements, and gives us a robotic system that can learn in one shot just by adding vectors together.
You know, if we pull back and connect this to the broader history of computer science, it raises an incredibly provocative question.
Oh, what's that?
Well, for decades, artificial intelligence has focused heavily on mimicking the physical structure of the brain's neurons. We build neural networks by mapping artificial synapses and deep layers to mimic the visual cortex. But Canerva's research forces us to ask, what if the true secret to human-like cognition isn't just in the physical wiring?
What if it's the math itself?
Precisely. What if it is the geometry of how the data is encoded? There is growing evidence that HDC closely mimics the distributed, high-dimensional data handling of the human cerebellum. Perhaps the next giant leap in artificial intelligence isn't just about building bigger and bigger networks with trillions of parameters.
Yeah.
Perhaps the real breakthrough is learning to compute in an entirely different geometric reality altogether.
A completely different geometric reality.
Uh,
So next time you're out somewhere and your phone battery dies because it's trying to process a heavy AI task, just imagine what it could do if it was thinking in 10,000 dimensions instead. Thanks for taking this deep dive with us.